Okay, hi there. This is our fourth asynchronous meeting. I hope you're all well, and I hope you're enjoying your summer. So let's talk a little bit about probability. Probability is a measure of likelihood, so it's how likely is an event going to occur. Um, this is not technically part of statistics. It actually falls under like game theory, but it's something that we use in statistics to get something done. So you have to imagine likelihood as being, okay, this is a unit, this is over here, like not happening. So there's no way, it's impossible, it's not going to happen, and this is absolutely going to happen. And over here we put 0, and there we put 1, because if it was a digital world, it didn't happen. 0 and 1, it did happen. Little tiny tidbit. The power switch on your computer is actually a 1 inside of a 0. The 1 being on and the 0 being off. And that's why that's the international symbol for that. But okay, that's a little math trivia there. All right, so anyway, probability runs from 0 to 1, but we put it on a spectrum because things can be anywhere in between that in likelihood. So that's what we got. We take events and we break them down into the results of procedures. So basically, in a probability thing, we have a procedure, something that we do. And when you do that procedure, you get an event. So every time you do that procedure, an event will occur. Now, sometimes those events are complex, sometimes they're not. If we take those events that can occur and we break them down into their most smallest components, we call that a simple event. And that's the smallest possible thing that we can possibly break it down into. If you take all of the simple events that are associated with a given procedure, we call that a sample space. So if you take the probability of all the simple events, you should get 1. Okay, so we usually use capital letters to represent an event. And we say P of that capital letter is its probability or its likelihood of occurring. There we go, likelihood, there we go, of occurrence. So the idea here is that P is a function that eats A, it eats an event, it spits out a likelihood of occurrence when a procedure is performed. Now, this is where things get slightly complicated. So I'm going to get rid of all of this. All right, so we end up with 2 different ways of measuring this stuff that we call probability. And one is what is called the classical way of doing this, where if A is an event, right, and then this thing, the magnitude of A, is the number of simple events in which A occurs, right? So the number of simple events in the sample space where A occurs. S is the sample space, so this is all of the simple events that could occur, right? So the probability of A occurring is the number of different ways A can occur over the number of different ways the procedure can have outcomes, right? So here, you don't actually have to run the procedure. You have to examine the procedure and say, okay, these are all the possible outcomes of this procedure, and in this many of the outcomes, A has occurred. Okay, so this is classical. Classic example here is you roll a 6-sided die. There are 6 possible ways for the die to land, and if I want an even number, 3 of those, so the probability of getting and even on a six-sided die is 3/6, or 1/2, or 0.5, or 50%, depending on your ilk, right? So we never actually had to roll the die to actually make that make sense. So the other way of viewing probability is experimental. And here you actually conduct an experiment. You actually do the procedure over and over and over again. So in experimental probability, you do the procedure n times. We call that the number of trials. And then we see how many times does A happen. So the probability of A is going to be the number of trials where A occurs over the number of trials. So if there is a disagreement between the experimental probability and the classical probability, the one that you trust is the experimental one, because this is what is actually happening. This is only a model. So this models that. Now that's a tricky one, because a lot of times, like, we want to say trust the math, and well, if the math doesn't line up with reality, you shouldn't trust the reality. So the example that I give to the students is like you're flying a plane. If you're looking out the front window of the plane and it looks like you're going to hit a mountain, and the instruments say you're going to fly over the mountain, you should assume you're going to hit the mountain because it's safer. So you go with what the experiment's telling you, not what the model or the instrument is telling you. All right. Now, if the model is accurate, then we get what's called the law of large numbers. Law of large numbers basically says that if I take the limit as the number of trials approaches infinity of the experimental probability of A, that should be the classical probability. So if the model is accurate, right, then we should get convergence there. And that should happen after about 30 or 40 trials. You should start seeing that. So the distance between these values is what's called the precision. But if it's converging, then we say that the model is accurate. Because of human error and limits of our ability to measure, there's going to be a limit to the precision that can't be overcome without using, an advance in technology. Some things to be aware of, like if you're doing computer precision, you only get 15 to 16 decimal places. That's kind of a big deal in like measuring small precision things. It's just because of the way a computer represents binary numbers. You can do like a whole course on that. But also you end up with situations where the classical probability is irrational, which is like kind of a neat thing to point out. So like, let's say you have, all right, so let's get some space here to draw. So let's say you have a square. Okay, you have a square. And you have a circle inscribed in that square. And you're going to throw darts at random. Okay? And we want to know what is the probability of landing inside the circle given that we hit the square. Okay, so the classical probability here, so let's say that this is the radius of the circle r, right? So that means the side of this is 2r, which means the area of the square is 4r squared, which means the area of that circle is pi r squared, which means that the probability of hitting the circle, given that we're in the square, is pi over 4. This is irrational. Okay, so what does that mean for us here? Well, that means that if I try to take the experimental probability and I start actually throwing darts, okay, well, then I'm going to get a number of darts in the circle over a number of darts thrown. And that is going to give me an integer over an integer, which is rational, which means that no matter how hard I try, this number will never equal that. To me, that's like fascinating, and it's kind of like deep in the mathematics there. But this is a point we're showing that the experimental and the classical probability in this case can never actually be equal because they're mutually exclusive sets. All right, speaking of mutually exclusive sets, let's get into some more of the thinking here. Okay, a mutually exclusive set are mutually exclusive events are events that one, cannot occur at the same time, and two, one of which must occur. Okay, so like if I have my Venn diagram here, mutually exclusive events are going to look like this. So this is the sample space. Either A will occur or B will occur. They cannot both occur, and they are but one of them must occur. So these are what we call mutually exclusive events, and we can call them complements. Okay? So I take that back. Mutually exclusive events they can't both occur. If they're mutually exclusive events and one of them must occur, then they're complements. There we go. So like you could have a sample space here where you could have A and B, and these are mutually exclusive. But they're not necessarily complements. Here, they're mutually exclusive and they comprise the whole set, so this makes them complements. So like heads and tails are complements. So we can actually, in this case, say that B is the complement of A. We use a little bar like that. Which also means that the probability of the complement is 1 minus the event. Right, so sometimes it is pretty, pretty tricky to calculate an event, but calculating its complement is oftentimes easier. Okay, so like if you take an example, like what is the probability of getting at least one question right on a 20-question test? Okay, that's multiple choice. So let's say it's multiple choice and it has 4 choices. 1, 2, 3, 4. And there's 1, 2, 20 questions. So what's the probability of getting at least one right? That's kind of hard to do. But getting the probability of getting them all wrong, okay? So like the probability of getting the first one wrong is 3 out of 4 if you're blindly guessing, right? And there's 20 of them, so that's 3/4 to the 20th, right? Pen's doing me in here. I'm wondering why. Let me pause for a moment. So 3/4 to the 20th, which like is a really, really, really tiny number. Let's bring up a calculator and look at that. What's that? 3/4 to the 20th power is that, right? So that's the probability of getting every single one of the questions wrong. But the complement of that would be getting at least one of them right. So if I take 1 minus that answer, then I have a 99.6, almost 99.7% chance of getting one of those right. Now, I didn't go through and figure out what's the probability of getting 1 right, what's the probability of getting 2 right, what's the probability. That's like way complicated, but I used the complement to help me there. So this is a little trick that we use with probability. All right, so that's complementary events, right? They're mutually exclusive and they comprise the whole. So if you add up their probabilities, you're going to get 1. Where things get interesting is when we get compound events, right? And this is where like the Venn diagram game comes in. So compound events are events that combine 2 or more simple events, right? So usually we get like the nice neat Venn diagram here where you have a simple event A, a simple event B, right? And then we look at it. So I'm going to make a second one over here because this is interesting. And I'm actually going to make a third one down here because this is like something that happens mathematically, but nowhere else. All right, so if we're doing a union, right, A union B, then that's I'm in A, I'm in B, or I'm in both, right? So this would be A union B. The note, if the events are mutually exclusive, then the union is empty. So if the events are mutually exclusive, the probability of being A union, sorry, that's not correct. Don't do that. I'm getting ahead of myself. A union B. Let's talk about that. A intersect B. That's it. That's the one I'm trying to get at. That's just here, right? So that's A and B. So this is or, this is and. This is where we have the mutually exclusive problem. A and B here are mutually exclusive, which means that the intersection, the probability of being in the intersection is in fact 0. It's impossible, right? So that's a test for mutual exclusivity. The one that bothers students is the fact that the both is included in the or, because we don't do that in the English language. We either say it's red or blue. We don't say it's red, blue, or both. In math, they actually use this term somewhere deep in things called XOR, which is actually A, B, but not in the intersection. We don't tend to study that in probability, but it does come up like in computer sciences. Sometimes you'll get this XOR idea. So just if they ever wonder, there is a word for it. It's the XOR, okay, or the union less the intersection. All right, so in the intersection, we say that the probability of the intersection is follows what we call an addition rule, which is the probability of being in A plus the probability of being in B. Sorry, I'm off base there. Not the intersection. The probability of being in the union, there we go, of being in the union is related to the intersection. It's the probability of being in A plus the probability of being in B minus the probability of being in both. The intuition behind this is that if you're counting everything that's in A and you're counting everything in B, then you're counting the intersection twice, right? So what you have to do in order to get the probability of being in the union is you have to remove one of the intersections. It's a pretty simple, straightforward idea here. I did this with a two-way table, right? So we've got this idea that people are either using or not using drugs, and they're either testing positive or negative, right? So if we're looking at that, we've got a total of, I think, 1,000 people in my table here. 1,000, there it is. All right, and we're looking at this, and we've got here the probability of the intersection. So A is going to be drug users, and and P is testing positive. So these are the people who are either drug users or testing positive, right? So this is the probability of A here, right? The probability of A is going to be 46 out of 1,000 are drug users, right? This is the probability of testing positive, 44 in 90. Should be, whoops, that's not right. 134. Let me go fix that in the notes. All right, so just like magic, we fixed it. 134 is the probability of drawing. So that's the probability of testing positive, And this is the probability of the intersection, right? So there's 44 out of 1,000 people are in the intersection. So this means my probability is going to be 136 out of 1,000, or 13.6% of my folks, right? So literally the kids eventually, if you give it to them in 2A tables, figure out that their answer is add the 90, add the 44, and add the 6, but don't add the 44 twice. And that'll get you to that 136. So if you look at something like that's mutually exclusive, right? Remember, when you're mutually exclusive, the probability here is going to be 0. So like if probability of, let's say, M and N are mutually exclusive, the probability comes up at 0. So like we've got here the probability of using drugs in positive. So that's 44 out of 1,000 are positive testing drug users. 860 out of 1,000 are negative testing non-drug users. You cannot be in both of these categories at the same time. So we don't have to worry about the intersection, and we just add it all up. And we get 90.4% are in that category. All right. So this brings me to conditional probabilities, which is where things get fascinating. Let's use that same 2A table, right? What we want to know here is what is the probability of being in one set given that we're in another. So if I look at my 2A table here, I know I have 134 people, right? 44 plus 90 that got positive drug results or positive tests. So given the P, the positive test, what's the probability that I am a drug user, right? So out of the 134 people who got the positive test, the probability that the number that are actually drug users is 44, which means that my test results are 32.8% of the time. So 32.8% of the time somebody here tests positive for drugs, they are an actual drug user. This is a horrible test. We should never use this, right? One of the ways to get the kids to see this is it's A over P. If you kind of turn this sideways, A is the number of drug users, 44. P out of the P, the number of positive users, which is the 134. Some kids find it easy to visualize it that way. So that gets you the conditional. This makes there's a relationship between the intersection and the conditional probability. The probability of the intersection is equal to the probability of the event times the probability of the conditional of B given A. Okay, so like if you work this from our 2A table, the intersection here is, well, the intersection of P and A is going to be 44, so that's at 0.044. The probability of just being a positive tester is 134 out of 1,000. And the probability of being conditional, which is what we just found here, is at 44 out of 134. Now, if you look, what's nice here is that 134 and that 134 cancel. Gives me that guy, and gives me that same value. So this thing holds. And this is like the useful one. Sometimes people write it also as P of B given A is equal to P of A and B over P of A. Note, it's the second part of the conditional is the denominator there. So this is a pretty useful little tool. It allows us to get through a lot of conditional probability problems. All right, so let's talk about a little bit of sampling and independence. Okay, so independence is I think I have it above here. Yeah, bum, bum, bum. Independence is a matter of conditional probabilities. So it's there. It's at the very top of it. If the conditional probability of something, so like if A given B is the same as the probability of A, right? So it doesn't matter whether or not B has occurred. The probability A is going to be the same. Then we say that A and B are independent, right? So this is different from mutually exclusive, right? Mutually exclusive is that the intersection is 0. Here, it's that the conditional probability is equal to the probability. These are not the same thing. All right, so that being said, let's drive down a little bit here into this idea about sampling and independence. Okay, so we get in this idea of replacement and not replacement. Okay, so think about it this way. If you're sampling from a set, let's say I have a set with A, B, and C in the set, and I'm going to start sampling and I pull A, okay, and then I take A out, but I don't put it back, then I can't pull A again. So then I could pull B, right, put it back in C. So that's one possible outcome, and like B, A, C would be another possible outcome. And we'll get into combinations of permutations a little bit later on where we start counting these things. But this is without replacement, right? If I can replace, then like I could get A, B, or B, A, C, or B, B, C. These are places where, or I could just get 3 C's. This is where the same thing can come up over and over again. All right, so this has an idea here. So the trials here are dependent, right? So the probability of getting A in the second trial, given that I got B in the first trial, is not the same as getting the probability of A, right? Because this would be 50% as opposed to 33%, right? Here, though, they're independent. The probability of getting A in the second trial, given that I got B in the first trial, is the same as getting just pulling A. These are both 33%. So if I have no replacement, I treat it as though the trials are, oops, there we go. Wow. If I have no replacement, I treat it as though the trials are non-independent, right? Or another way of saying that is that they're dependent. So no replacement is non-independent. If I have a replacement, I have dependence. Now, this holds for like almost every case in the world. But we're going to create this thing that we're going to call the 5% rule. Okay? And the reason why we get the 5% rule is if I have a really large population and I'm taking a very small sample, it really doesn't matter if I'm replacing it or not. The likelihood of me picking the same thing twice is really, really tiny. So let's say I'm sampling like 4 Americans out of the whole like 350 some million, right? If I, at random, pick 4 Americans, it is really highly unlikely that I am going to pick the same American twice, and it works as though I'm like doing independent trials, right? It doesn't quite matter. Okay, so these two things come out the same. The one that's easier to actually calculate is with replacement, because you just follow the multiplication rule there and you don't worry about things. You just kind of take and multiply, multiply, multiply. Whereas if you are doing, if you're trying to do this as though you are dependent, right, you have to throw in the conditional probabilities. So you can ignore the conditional probabilities if the sample you're taking is less than 5% of the population. Okay? It's basically how we do it. It makes the math easier. It's one of these places where you kind of hand wave it at a little bit, but it just makes computations so much simpler. So that's like the break point for it, is if your sample is less than 5% of the population. All right. So let's talk about the that there are inverse conditionals. Okay, and this is what trips a lot of people up. So let's say I have the probability of A given B, and I have the probability of B given A. These are not equal. They're not. So this is like the probability of, I don't know, let's make it getting a ticket given that you are driving fast versus the probability that you were driving fast given that you got a ticket. Okay, like, okay, I can drive fast and not get a ticket. That makes sense, right? So not every time that I'm driving fast I get a ticket. Most days, probably not. Now, not every time I get a ticket am I driving fast. I could be like running a red light, something like that. So these two things are not equal. Okay, so there was a guy named, there's a guy in the 18th century named Nicholas. Nicholas Sanderson. So 18th century. He was a blind mathematician. There we go. And he discovered what later becomes known as Bayes' theorem. Okay, so Thomas Bayes was an Anglican minister who was attributed to himself something that he probably read in Sanderson's book. So literally, Bayes is a minister who stole from a blind man and put his own name on it. So we get to know this as Bayes' theorem, but Sanderson is the actual first person, and it's pretty well understood that Bayes actually read Sanderson's book. So there we go. So there's your mathematical tidbit. Bayes figured out the connection between, well, not Bayes, Sanderson figured out the connection in between these two things, and we call it Bayes' theorem. And it tells us that the probability of A given B is equal to the probability of B given A times the probability of B. So the left one is up top over the probability of A. Now, proving this is actually really quite simple. So let's do that. You know, what the heck? Let's do a proof in math. Getting rid of all of this. And here we go. All right, so we want to prove that the probability of A given B is equal to the probability of B given A times the probability of B over the probability of A. Okay, so note, the probability of A given B times the probability of A is equal to the probability of A and B. Oops, A and B. We established this earlier. You can look up in the notes, it's there. If you take the probability of B given A times the probability of B, this is equal to the probability of B and A, which B and A is the same as A and B, which these two things are the same thing, which means that this thing is equal to this thing, right? Sorry. So if we put PA given B times PA equal to PB given A times PB and divide both sides by this PA, we're going to get PA given B is equal to PB given A times PB over PA, and lo and behold, we've proven Bayes' theorem. Okay, so it works. All right, so like, what does this mean? All right, so I've kind of worked this out in a problem, and we're going to say that we have an election. Okay, and we know that the probability of getting a Democrat, given that we have a likely voter, is 40%. So I pick a likely voter at random, the probability that it's a Democrat is 40%. The probability of just picking an eligible voter at random who is a Democrat is 45%. The probability of picking a likely voter from the set of all voters is 30%. So this is like a horrible voter turnout, right? So one way to intuit this is to build a two-way table, which is what I did in the notes. Okay, so, and to pick a large number, so like I like 1,000. All right, so we have the Democrats and the non-Democrats, right? We have the likely voters and the non-likely voters. All right, so out of the 1,000, 45% of them are Democrats, which means there's 450 Democrats total. Out of the 1,000, 30% of them are likely voters, which means that there is going to be 300 likely voters out of the 1,000 total, which means 700 are not likely to vote and 550 of them will not be Democrats. All right, we know this. The probability of getting a likely, okay, once we have a likely voter, so out of these 300 likely voters, the probability that we're going to get a Democrat, right, so the D's, is going to be 40% of that 300, which is 120 of them. Now you can fill in the rest of the table, because if this is 120 and that's got to add up to 300, that's got to be 180. If this is 120 and that's 450, that's got to be 330. And if this is 180 and that's 550 or 330 and 700, this has to be 370. And that's where the 1,000 voters lie. So given this 3 pieces of data, you can actually, and the size of the population, you can actually build the two-way table. So what we want is the probability of, given a Democrat picking a likely voter. Well, the number of Democrats is 450 in my population. The likely voters are 120. And so let's grab the calculator here. That's 120 divide by 450 gives me 26 2/3%, right? So this is 0.2667. Now, let's play this off of Bayes' theorem, right? So, I'll scroll up here a little bit. If you think about Bayes' theorem, it tells me that the probability, I'm going to write it up here, the probability of L given D should be equal to the probability of D given L times the probability of L, right, over the probability of D, which we know this is 0.40 times 0.30 over 0.45, right? So we grab for the calculator again, and we take 0.4 times 0.3, right? We divide that value by 0.45, and lo and behold, we get that same 0.2667. So it all works out. Okay, so there's Bayes' theorem, there's the conditional probabilities, and how you get from one to the other. Bayesian analysis is something that we're always doing in stats because it's how we get from the wrong data to the right data given some additional information. This happens a lot in like things like drug trials and is oftentimes used in astrophysics. So there you have it. Let's talk about counting techniques. So this is the thing that comes up. This is balls and boxes, right? So this is what comes up all the time on like AP exams, not APs, SATs, ACTs. This is the questions that they're like, how come you never taught us this? And it's because we don't teach stats early on, and we probably should teach more of it earlier. All right, so the basis of all of this is if I have n balls in the box, right, and they're numbered like 1 through n, and I start pulling them out of the box at random, how many different ways can I pull that out? And this is what we've come to call n factorial, right? So the way we technically define this is we say 0 factorial is 1. Yep, if you put 0 factorial in a calculator, you're going to get 1. 1 factorial is 1. And then every factorial above this is you take the 1 before it, and then you multiply by n. So this is for all n greater than or equal to 2. We just basically tell the kids it's 1 times 2 times 3 out to n. So if I have 4 balls in the box, right, then I can pull them out 4 times 3 times 2 times 1 different ways. That's 12 times 2 is 24 different ways. Okay, so that's the basic problem, right? You have the order that you're pulling them out matters. You cannot replace the ball back in the box. You're going to do the whole set. All right, so a slightly more complicated version of that problem is I now have n balls in the box. I'm going to take r, which is less than n balls out of the box, and I'm going to put them in order. So like I have 1, 2, 3, 4, 5, 6, and I'm going to pick 3 balls. So I'm going to pick 2, 4, and 5, and I'm going to pick them in that order, or if I do it again, I pick 6, 1, 3. So this is different. These are what we call permutations, right? Formula for that is n factorial over n minus r factorial. Most of the students don't need to memorize this. They need to know where to find these things on the calculator, right? So the intuition here is the order matters. I'm not replacing anything, but I'm only taking part of the set, right? There's an easy way to remember this because permutations, the P, is actually the correct word for a combination lock. If you take the combination lock, you don't put all the numbers in. So you only take a subset of the numbers, but they have to be in the right order, which means it's not a combination lock. It's a permutation lock. So if you can get them to remember that the combination lock is the wrong thing, and if the order matters, it's a permutation, that kind of helps me remember it, that the name of the lock is wrong. All right, so my little problem here, if I picked all 6 balls, right, that would be 6, and then I go math, probability, number 4 is the factorial. There'd be 720 ways to pick those balls, right? But only picking 3 of them. So I'm going to go 6, math, and number 2 is the permutations, and I'm picking 3 of the balls. So there's only 120 ways to do that. Now, why am I dividing by n minus r? All right, so if you think about this, if I pick the balls 1, 2, 3 first, then the other ones, 4, 5, 6, don't matter. So it doesn't matter what order these other ones come into. These permutations are all the same because I only care about the first 3 balls. Well, how many different ways can I order the last 3 balls? Well, that's n minus r factorial different ways. So I group these n minus r factorial groups together, and that's why I'm dividing by that here, right? So this is all 6 balls, and then the number of groupings that are the same because the last numbers don't matter is the denominator there. All right, so that's permutations. So we'll add another layer to this. So now what I'm going to do is I'm going to start with n balls in the box. And I'm going to pull out r, which is less than n. And I don't care what order they're in. If I pick 3 balls, it's those 3 balls. It's fine, right? So this is what we call combinations, NCR. So this starts with your permutation formula, right? So we're just going to start with all the permutations, but then we just divide again by r factorial. Okay, so in this case I have, let's say, 6 balls in the box. I'm going to pick 3. So I'm going to pick 1, 4, 6. 1, 4, 6. And then, see, here's the thing, is that like this is different from 2, 4, 6, because there's a 1 in this one and a 2 in this one. But this is not different from 6, 4, 1 or 4, 6, 1. These are all the same because I don't care about the order in which the balls came out. It's just I've picked the balls 1, 4, and 6. I'm not replacing the ball. I don't care about the order in which they came out, and I'm only taking part of them. So this is when combinations happen. This is why this is a combination lock is a misnomer. Because if you put 1, 4, 6 in the lock and the combination is 6, 4, 1, it doesn't open, right? So that's actually a permutation lock. All right, so anyway, let's do this. So this is the number of ways that I can order 3 out of 6 balls, right? That's the permutation thing. But now I don't care about the ordering of these. So how many different groupings of these are there? Well, there's r factorial groupings there, and that's why I divide by that again. So, all right, so this is another way to kind of visualize this, right? The last thing that we use is powers, right? So when you're dealing with a power situation, you've got like n different balls in the box, right? And you're going to pull r less than n out of the box. But now you have replacement. So I have like the balls 1, 2, 3, 4, 5, 6 in the box, and I'm going to pull out 3 of them. So I can pull out the 1, I can pull out the 2, but because I put the 1 back, I could pull the 1 again. Oh, okay. So I could say, okay, 3, 4, 4 could be a possible answer, or 3, 3, 3 could come up because these are, the replacement is happening here. So you kind of visualize it as the first ball can come out, n different ways. The second ball can come out n different ways. The third ball can come out n different ways. So this is n to the third different ways, or we visualize it as n to the r, right? So in this case, the order in which the balls comes out matters, right? Because like 1, 1, 2 is different from 1, 2, 1. So it's like permutations like that, but there's a replacement. So these are like independent trials, right? So this is a little different game. Now this is where they all start to gloss over, because it's all like, oh my gosh, I've got powers and combinations and permutations and factorials and all of this. So what I tend to do with the students is I tend to build a table. And I say order. Does it matter? Yes, no. Is there replacement? Yes, no. Okay. So the first question is like, okay, order matters and there's replacement, right? So that's the powers, right? Order matters and there's replacement. There you go. All right. Order matters, but there's no replacement. All right, so you get two answers here. N factorial is when you have the whole set, and NPR when you have part of the set. Now, here's the interesting fact. If you think about this, NPN would be N factorial over N minus N factorial, which is N factorial over 0 factorial, which remember we said earlier that N factorial is 1, so it just gives you N factorial. Aha! So if you have the whole set, this NPR reduces to N factorial anyway. So if they happen to plug in 6p6, they're just going to get 6 factorial. It works. This is why the 0 factorial has to be equal to 1, because otherwise we get division by 0 and bad things happen, and the math doesn't work. Oh, by the way, the factorial doesn't work. You can't have like 1.5 factorial. It only works on positive integers. Okay, so it only eats positive integers and returns positive integers. Okay, actually it works with 0 too, so it's non-negative integers. So let's do this. Integers where z is an element of the integers and z is greater than or equal to 0. Okay, so there we go. I digress. The other part of the table that we can get here is that we don't have replacement, but the order doesn't matter. That's NCR, right? So like dealing a deck of cards, you can't get the king twice, and this is not in this course. They love when I do this. You don't typically deal with this situation often. It doesn't come up a lot. And it's not really the subject matter of a basic statistics course, so you leave that one alone. So I tend to build this table with them, and what a lot of them do is right before the test, they all sit down and they take out the test, and they write down that table so they remember what is what. So I hope this helps with your understanding of probability. I'm going to go back through a little bit with conditional probability, Bayes' theorem, and counting techniques when we meet in person on the 15th, because they're like confusing, and this is the places where kids get hung up. And there's stuff that matters. There are questions that come up on like the SATs and ACTs and things like that. So I'm hoping that you're still finding this helpful. I know that it's a lot, but we'll see each other in a couple of days here, and we'll go from there. All right, thank you.